everybody, this is Dr. Fu. This week we're going to talk about Module 6b. We're going to measure the conduction velocity on human subject. These are the objectives. And here is a chart showing how the action potential drops when it's travel along an axon. So this is the original height, and it's going to eventually disappear. But before it disappears, will reach 37% of the original height, which is dropped by 63%. Okay, does this number recall anything? Alright, here's the equation that we've been talking about in Module 3. Do you recall that? Okay, so what did the first equation tell you? This is the Lance constant, right? So the Lance constant is the distance that action potential travels from its original height to 37% of the original height, dropped by 63%, right? So the distance from this point to this point, we call that Lance constant, right? And then there's another equation tells you the time constant. The time constant is the time cost for action potential to travel along this axon until it reaches 37% of the original height, dropped by 63%. So the time cost from here to here when the action potential travel along axon, we call this time constant. All right. So now we have Lance constant and time constant. Okay, and they both start from here and ended up in here. What can you calculate based on these two numbers? We got distance, we got time, then we got velocity. Is that right? So basically, you got velocity distance, which is your Lance constant, divided by your time constant. You get your velocity. And we simplify the equation, we got this. Okay, so from this equation, we can know how the factors changes going to affect neurons' conduction velocity. Okay, so here let's talk about how can you increase the conduction velocity on a neuron. First one, you can increase the diameter, right? Because based on this equation, the diameter is here. If you increase this number, the velocity will change, right? Will increase. And if you decrease the membrane capacitance, which is C here, you are also going to increase velocity. And how do you decrease membrane capacity? The answer is by myelination. So the thicker your myelination you have, the faster action potential is going to travel along this axon. So there's two other factors. One is Rm, the other is Ri. Ri is internal resistance. It's related to environment temperature, cell content. These two factors are pretty much fixed. They don't vary that much. And then Rm is the number of channels that you have on the cell membrane. That's the membrane resistance. And these numbers don't vary that much either. So basically, you have two factors that affect action velocity a lot. One is the diameter, the other is myelination. Okay, so since myelination is a good thing to increase our conduction velocity, is that a good idea if we have the whole neuron myelinated? The answer is no. Why is that? Because if your whole neuron have myelination instead of have some naked spot, the action potential is going to drop as it travels along the axon. So the action potential will deteriorate. You don't want that happen, so there's going to be some open spot. These open spots are for these action potentials to replenish. So it's important to have naked spot on the myelinated neuron. And this naked spot, we call them node around VA. That's a naked node. Because of this node around VA, signal travels along a myelinated neuron. Looks like signal is jumping in between these node around VA. So we gave them a name for this type of neuron signal traveling. We call them salutary conduction. Okay, here's an image showing how the action potential travels. This is action potential travel along a myelinated neuron. See, the action potential travel pretty fast. It doesn't deteriorate it because the node around VA you have replenished of action potentials. And this one, action potential travels along a naked neuron. Signal travels pretty slow and eventually dies out before it can reach the terminal. Alright, so in the last 3 weeks, we've been record action potentials directly from nerve cord, from cockroaches, from cricket, from earthworms. We either isolate the nerve cord out or we put a pin electrode to collect signals directly from nerve cord. Well, this week we also need to collect action potentials from nerve cord, but we don't want somebody to isolate our nerve or pin a nerve cord for us. Is that right? Okay, so we have alternative method to measure conduction velocity on human subjects. So the alternative is EMG, electromyograph. Myo means muscle. EMG will record signals from a contracting muscle. And in the neuron, in the nerve cord, you can record signals because nerve cord has action potentials. So here's the question, does muscle cells also have action potential? The answer is yes. Otherwise, we won't be able to have EMG. Basically, EMG is recording action potentials from a contracting muscle. Okay, so we're going to have 3 experiments in this lab. The first one, we're going to measure the conduction velocity on the median nerve. So where is the median nerve? If you make a fist, okay, you're going to have some tendon. Somebody don't. Most of them will have tendon. So on the thumb side, you are going to have your median nerve. It's this nerve. Okay, what is the function of the median nerve? It controls your thumb, your index and middle fingers, and a little bit here too. And today we're going to record muscle activity from this muscle. A doctor places Brevis using EMG. And what this muscle do is going to abduct your thumb. So if this muscle get activated, it's going to move your thumb this way. Abduct your thumb. Okay, we need to put some electrodes onto our subject in order to collect information, right? And there are so many of them here, and what is the function of each of them? So these things, we call them stim bars. These things will generate electricity, will shock the median nerve runs along here. Once the median nerve receives electricity, is going to be excited. The nerve will send signal to this muscle, abductor pollicis brevis, and this muscle will twitch. So you are going to see some movement of this thumb, and by the time when this muscle is activated, these 2 electrodes will record signals from this muscle. This electrode here, the green one, is more for ground. Okay, same thing for the earthworm. We have the ground electrode. Okay, well, we need to measure the conduction velocity. For conduction velocity, we need 2 things. One is the distance, the other is the time. The distance is from the injecting site to the recording site. So this is the injection site, this is the recording site. Okay, so we're going to measure the distance from the stim bar to the Y electrode. And then how do you measure the time? Alright, so here is the lab chart you are going to see, and this is how you measure time. Same thing as last week and the earthworm. If you inject a current into the subject, you are going to have a stimulus artifact here. And this is going to be your action potential from the muscle. So the time that you measure is from here to here. Okay, so that sounds like a valid experiment design, right? However, there's a experimental design flaw. What is that? So the time that we've measured on the lab chart is actually a sum of 3 parts. And only one of them is the one that you're supposed to include in there. Okay, so let's take a look. First one, T1, is the time constant for the electricity to reach the nerve cord, because there is skin, there is muscle for the electricity to penetrate, to go to the nerve cord, right? But this time is very short. The electricity travels very fast in tissues, right? So we can ignore that. T2 is the action potential travel along this median nerve. This is your median nerve. Okay, this is the real time we're supposed to use. There is a T3 here. T3 is the time that muscle recruit. So once this nerve gets activated, there is some neurotransmitter has to be released, and then muscle have recruit all these fibers to contract. And that way we can record signals from our electrodes, the action potential from muscle. So this T3 is fairly long. So this time we're supposed to exclude. So ideally, we need to exclude T1 and T3 from our T. This is our T, right, the time. But we cannot. So because the T1 is very small, so we can ignore that. However, T3 is still there. So we're going to bring some experimental errors by T3 in there. Okay, so for experiment number two, we are going to measure the conduction velocity of the sciatic nerve when the subject is having Achilles reflex. So what is really happening here? We're going to stimulate the Achilles tendon here, and then the subject will receive signal. The signal will send through the sciatic nerve, go all the way to their S1 segment of their spinal cord. And then the spinal cord will send signal back to their calf. So their calf will contract. And this signal sending back through sciatic nerve. Once the calf is contracted, we will be able to receive signals through our EMG electrode. And at the same time, we are going to still have a ground electrode, which is attached to your hand, the same as experiment number one. Okay, here's the image of S1 spinal segment. It's on top of your sacrum bone. So this is the sacrum, and this is your S1 segment of your spinal cord. The landmark of the S1 segment is your hip bone. So the top of your hip bone is pretty much where your S1 segment is. So the top of your hip bone will give you a landmark of how do you measure the distance for this experiment. So you need to measure the distance from your Achilles tendon to S1 segment, and from your S1 segment to your calf. So there's two parts of distance that signal travels, because the signal is received from Achilles tendon, go to your S1, and from your S1 come back to your calf. Okay, let's talk about how do you measure time for this experiment. So the time is when your hammer hits subject's Achilles tendon till when you see signals on the calf of the subject. So the time between here and here is the time that you need to use to calculate your conduction velocity. Okay, so for experiment number 3, it's measuring the conduction velocity on multiple nerve. It's a voluntary movement, right? So for this experiment, all the settings are going to be the same as experiment number 2. The only difference is when the subject here, the hammer hit on the table or somewhere else, is the subject's going to point his or her toes. Okay, so the time you're going to measure is the same thing from the hammer hit the table until you see the first peak that appear on the recording site, and that's the signal from the calf. Here in this experiment, you are going to see many peaks. Distance to measure. Let's think a little bit about how the signal travel for this experiment. The subject will point their toes when they hear the hammer hits, right? So the signal basically travels from their ear and then to their brain, and their brain tell the spinal cord send signal to their sciatic nerve, and then the sciatic nerve goes to their calf. So that is how signal travels during the whole procedure. So we need to measure the distance from the ear to the brain to the spinal cord, and then all the way to the calf, right? But it's hard to measure that detailedly, so we're gonna round it up to just measure the distance from the ear to the calf. Okay, so that is the lecture part.